In this CPR, I'm going to go over the parallel plate capacitor problem from exam 3. We have a 4-volt battery attached, an initial plate separation of 0.002 meters, free space between the plates, and an initial stored energy of 2 joules. Then the battery is removed, and the plates are moved closer to 0.001 meters without disturbing the charge on the plates. Fringing can be ignored. We're asked how much energy is stored after the plates are moved, and where did the missing energy go? So for parallel plates in free space, the field satisfies V equals E times D, with D being the plate separation. So we can find that our initial electric field equals V over D, which equals 4 volts over 0.002 meters, or 2,000 volts per meter. We know that the energy density in free space is equal to 1/2 epsilon naught times the electric field squared. So to get our initial total energy, we multiply the energy density by the volume. And the volume is equal to the plate area S times our plate separation D. And we're told that this equals 2 joules. So once the battery is removed, the charge cannot change. So the total charge on the plate stays the same. So we can write that QF equals QI. And we know that the surface charge density equals Q over S. And since Q and S don't change, the surface charge density also stays the same. So we can write that the final surface charge density equals the initial. And flux density equals the surface charge density, so we could write that dF equals sigma F, which equals sigma I, which equals dI. And in free space, flux density and electric field are related by D equals epsilon naught times E. Since D stays the same and epsilon naught is constant, the electric field must also stay the same. So we write that the final electric field equals the initial, which again equals 2,000 volts per meter. But even though the electric field stays the same, the voltage does not. And that's because the voltage equals the electric field times the distance. So our final voltage equals the final electric field times our new distance. And because the distance is halved, the voltage will also be halved. Get that. Went from 4 volts to 2 volts. So having the distance halves the voltage, but the field does not change because the charge is fixed. So the energy density only depends on the electric field, and the field stayed the same, so the energy density is unchanged. Where EF equals EI. But what does change is the volume between the plates. So our initial volume, S times DI, is twice of the final volume, S times DF. So since DF is half of DI, the volume is cut in half. So we can write that SDF equals 1/2 SDI. So the final energy must be half of the initial energy. So WF equals SDF, which equals 1/2 SDI, which equals 1/2. Sorry, forgot the energy density. Put the energy density in there. Which equals 1/2 times 2, which equals 1 joule. So our final piece to this problem is where the energy came or went from. So originally the capacitor stored 2 joules, and after moving the plates, it stored only 1 joule. The missing 1 joule became mechanical work. Opposite charges attract, and when the plates moved from 0.002 meters to 0.001 meters, the electric force pulls them together. That force does mechanical work, and the electric field loses that same amount of energy. So the missing energy was converted into mechanical work as the plates move closer together. So to wrap up, this problem highlights a broader idea that shows up throughout electromagnetics and in real engineering systems. Capacitors don't just store charge, they store energy in an electric field, and that energy can convert into mechanical work when fields change. Anytime we change the geometry of a capacitor, like the plate spacing, the area, or the dielectric material, we're really changing how much electric energy the system can hold. That's the same principle behind many electromechanical devices. Those devices rely on converting electrical energy into mechanical motion or vice versa. So this very simple parallel plate capacitor problem is actually the foundation for understanding how electric fields can produce forces and do work in practical real-life systems. It's a small version of the same physics used in actual engineering components.